In this problem, we have a student or a person who is playing catch with a friend. So this has similar characteristics to the problem we did yesterday as our example. In yesterday's example, you were given the initial velocity and had to figure out how long the ball would take to get to this point. In this problem, you were given not the initial velocity, but something else just as equally as good. The ball is being thrown from the ground, and your friend is 10 meters above you. We don't know the initial velocity of the ball. That's not been given. But we are asked what is the minimum speed at which you can throw the ball for it to rise to 10 meters. The minimum speed would be the speed where the ball makes it to 10 meters and stops. You throw it any harder than that, it will go higher, and any less, it won't go that high at all. So the minimum speed would be the speed to get it to the 10 meters. So you're being told the final velocity. It's not directly being given to you, but it's being given to you in a more subtle way. Once you recognize that, the rest of the problem should fall together pretty easily. This is a free fall problem, so we can use the acceleration due to gravity as 10 meters per second squared. Moreover, there's no reason, good or bad, to choose up as positive or down as positive. So doesn't matter to me. What would you like up to be? Positive. So now I identify the vectors, and I'm going to go upwards positive 10 with a downwards acceleration of 10 meters per second squared. Pretty straightforward now? Okay. So yeah, you're solving for this. That's a pretty good push. You're okay? And that's how you get the fourth piece. Or third piece. Next. I think number 4 is worth talking about. So if you haven't started number 4, and I like this problem quite a bit, and I want to talk to you a little bit about it because I think it's interesting. The other ones bore me. So in this problem, the first part of the problem, not very interesting. The pebble is dropped, and you're told that you hear the splash 7 seconds later. That's a pretty straightforward free fall problem with delta x, initial velocity of 0, final velocity unknown, an acceleration of 10 meters per second squared. Again, it's a free fall problem, so we're using the acceleration of gravity, and we're given a time of 7 seconds. Regardless of what you choose here, you'll find that the displacement, the distance the rock falls before reaching the water, is like 245 meters. So if you've done the math on it, that's what you should get. And that's just saying downwards is positive, put the positive there, and work the problem. 1/2 at squared plus v naught t. So 1/2 of 10 is 5, 7 squared is 49. Do some math and you can get your value for how far it is. That part's not particularly interesting. The next part's kind of interesting though. I like the next part. In the next part, they say that you have to take into account the fact that sound travels at its own speed. So the 7 seconds includes the time it took the pebble to reach the water and the time it takes the sound wave to come back up from the water and make it to your ears. Now they tell you that sound travels at a speed of 340 meters per second, which is constant. So the propagation of sound doesn't accelerate, not under the conditions of this problem. Now, if you look over here at your motion equations, and I'm only bringing this up because under this circumstance, maybe you didn't know this, but you could have figured it out. If the acceleration is 0, well, that means that the initial velocity equals the final velocity. That's kind of a duh. If there's no acceleration, the velocity doesn't change. But also, if the acceleration is 0, these two terms disappear. And you just get distance equals rate times time, the middle school formula for physics. And that's what you have here. Distance equals the rate at which sound propagates times time. Here's the thing. The pebble must take less time to reach the water than 7 seconds, right? Because the 7 seconds includes the time it takes the pebble to reach the water plus the amount of time it takes for it to come back up. So clearly, the bridge is less than 245 meters tall because it takes less than 7 seconds for the pebble to reach the water. Now, we don't know how much less. However, we could suggest that the time it takes the pebble to fall is 7 seconds minus t, minus the time it takes the sound to come back up. If we do that, this creates two relationships that have both displacement and time. Well, the pebble travels the same distance as the sound wave, so these two are equal. And t represents the time it took the sound wave to travel, so these two t's are also the same. You have two equations with two unknowns, and you have a cadre of ways of dealing with that. Pick your favorite. I would probably choose substitution. In fact, I would probably set 340t equal to 1/2 times 10 times 7 minus t squared. Now, this is going to figure out how long it takes the sound wave to come back. But once you have that, you can figure out how tall the tower is. How tall the bridge is. I'd say that's a pretty hard reach. That's a good one. That's a good problem. Has a lot in it. And I've given away all of the good stuff. All you have to do now is do the arithmetic for it, maybe a little algebra. But that's the kind of thinking it takes. Look, we're not going to have 1,000 problems of you plugging in numbers into one formula and solving for the one unknown. And if you want those, the book is filled with them. And the answers to those problems are in the back of the book, all the odds. So if you checked out a book from me, practice those. Somebody came at me with problems they found on the internet, and they wondered if they were okay to use them. Sure, I don't care. You better hope the problems that came with the answers have the correct answers. That's all I would encourage you to do. But the book has these problems in it. Chapter 2. All right. The cyclist problem is number 7. And you had this problem already at the very beginning of the year. It's just a slight modification. In the problem, we're told that a cyclist is traveling at a constant speed of 10 meters per second. And at a moment in time, they pass another cyclist who's traveling at 5 meters per second. At the instant the two cyclists are together, the second cyclist, number 2, is like, I'm not letting that guy beat me. And so he begins to accelerate at 1 meter per second squared. Now, if you are thoughtful about this, he's eventually going to at least get up to the same speed as the first cyclist, then be going faster, and likely will pass him as long as the first cyclist never changes their speed. And like I said, you've kind of seen this one because you saw something similar. Oh, Mr. Shelton. Cyclist number 1, traveling at a constant speed, if this is position and time. Cyclist number 2 has half the initial velocity, but is accelerating. The parabola suggests eventually they're going to be at the same place at the same time again. Now, this problem's not, once you understand that part, this problem kind of falls together pretty fast. The first cyclist, their delta x is going to equal 10 times t. They're traveling at a constant speed. The second cyclist, however, they have an initial velocity of 5 meters per second and an acceleration of 1 meter per second squared. Again, we don't have enough information here to actually solve for any variable, but we can put together a relationship that also has displacement and time. Correct? Two equations that share similar variables. I want to find the place where the displacement and the time is the same for both cyclists. On the other hand, you could just make this, put this into your TI as y equals 10x, put this into your TI as y equals a half x squared plus 5x, and let the calculator do the work. Right? Why'd you buy those TIs if you don't want to use them? But the calculator will do this, right? So will Desmos. You go, right, get the app, go to the website, put both equations there, it'll show you where they intersect. But I'm a purist and I don't go for the fancy stuff. I would probably choose the substitution method here. I think it's probably one of the better methods. And the only reason I'm continuing this is because you guys tend to make a mistake that bothers me greatly. Do you see what I've done here? Straightforward, one-step substitution. They were both solved for delta x. Why not just set them equal to each other? Now, if I do that, here's where the mistake gets made. You can't divide by t. I know you want to. Please stop. This is a quadratic and a very simple one. It's factorable. You need to factor. I know a few of you think that this is just a glorified math class, but I want to point out something to you. You don't go to math class, you can see numbers. Math was created for these purposes. And so it wasn't like we said, well, we're just going to make numbers so kids have a class to go to. When you factor this out, you're supposed to set both of them equal to 0. And the reason why you can't divide by t is because you're dividing by 0. That's why you have to factor and set the individual factors equal to 0. Now you might say, Michelle, that's not a big deal. Why are you... There's two answers here. And you should understand why you get two answers, because both of them are valid answers. You may not want both of them, but you must understand what the math is telling you. The math is telling you when the objects are at the same position. And they were at the same position at time equals 0, and they are again at the same position at time equals 10 seconds. Which is why I want you to do your math correctly. Don't cut the corners. Be thoughtful. You're easy to trick in the future. Be less so by doing your math thoroughly, please. Right, and you can do this math, right? The train problem. I know it's Friday. If you want a secret to the train problem, I can do it in a single drawing. One difference in the train problem, they both have accelerations. That doesn't change it. You just get two expressions with a t squared in it. The real thing about the train problem, though, is that they give you a separation distance and ask where they meet. So, to use this for this problem, this train goes a distance d, this train goes a distance 1,000 minus d. Make this the delta x for this train, and this the delta x for that train. You're still going to set d as your substitution variable and solve for t.